This is Mrs. Schroeder. We're back to talk about Chapter 11 in our Honors Chemistry class. Our objectives today are to talk about molar enthalpy of fusion and molar enthalpy of vaporization. We're also going to learn how to use these to actually do some calculations that apply to changes of state. When we're melting something or boiling something, vaporizing something, we have this energy change associated with it. We're going to learn today how to do those calculations. So we know that if we have a block of ice, we have to add energy to it to make it melt. If we have a bowl of liquid, it doesn't just boil on its own. It'll evaporate eventually on its own, but it needs to have energy added to get to a boiling point. So if we want to figure out how much energy it will take, we have a calculation which involves melting something, figuring out how much energy it was added, and we call that the enthalpy of fusion of a substance. And it's written in this delta H of fusion, FUS. F fusion stands for melting or freezing something, fusing something together into a solid, or breaking that solid apart. When we're vaporizing something or condensing something, we call this delta H of VAP, vaporization. The energy of vaporization, as you can imagine, is much greater than the enthalpy of fusion. And imagine what those, we'll take water for example. Imagine what the water molecules are going through. When they're a solid, they're in a very structured, packed arrangement. When we add a little energy to it, you can break those forces holding them together, those hydrogen bonding forces, but you don't need a lot because you're not really moving them really far. They start sliding past each other into a liquid form. When I vaporize something, I have to take those particles and move them very, very far apart, which means I have to add a lot more energy to break those bonds. So molar enthalpy increases as the substance's temperature increases. How much enthalpy or total energy of the substance is dependent on temperature. And right here this graph shows you molar enthalpy, and it shows us that as a material moves up this line, it has more internal energy. That's what enthalpy means. Now again, it was hard to measure the total energy of something. It's easier to measure the change in it. This area right here, which is this line, is considered the energy of vaporization, which is the vaporization at the boiling point minus the enthalpy of the liquid at its boiling point. It's how much energy was required to turn it from a liquid into a gas. And down here, again I'm looking at enthalpy over here, this is the heat of fusion, is this difference in enthalpy that it took to change it from a liquid to a solid at the melting point. So if I want to figure out how much energy would be added to fully vaporize a liquid or melt it at its melt a solid at its melting point, I'm going to use that enthalpy of fusion or enthalpy of vaporization and multiply it by the amount of the substance. So, for example, how much energy did it require to melt something would be the amount of substance times the delta H of fusion. How much energy is required to heat something, vaporize something, would be the N times the delta H of vaporization. Now again, be careful because sometimes with the units they might use grams or they might use moles. Check what they give you the delta H in to figure out if you need to have moles or you might have to use mass instead. Example, how much energy is required to vaporize 3 grams of ethyl alcohol at its boiling point? And they would give you this. This would be given. Or a way to look it up. But you wouldn't have to know what that is. So Q equals, in this case we're using M because we're given the vaporization in grams. So M times the delta H, and I get 2,511 joules is required to vaporize 3 grams. Another example, what mass of water will be vaporized by 33 kilojoules of energy? Delta H of vaporization of water is 40.7 kilojoules per mole. Now notice I have moles here and they're asking me about mass. So if I use this Q equals N delta H of vaporization, my energy is 33 kilojoules. N is what I'm trying to find. My heat of vaporization is given right here, 40.7. Its units are in kilojoules per mole. When I solve for N, 33 divided by 40.7, I get 0.818 moles. Again, it asks me for mass of that. If I have moles and I want to go to mass, you take your moles, 8108. I missed my 0 there. 8108 times its molar mass of water, which is grams per mole, 18. This is the molar mass of water. And when I calculate that out, I get 14.6 grams. This is the amount of water that will be vaporized if I add 33 kilojoules of energy to it. And if I were to take a scoop of ice or a scoop of snow from outside, this at negative 20 degrees. Initially it's a solid and it's cold. Before it begins to melt, I have to raise the temperature of this thing. So what you're looking at is if you begin to heat this along this curve, this is my ice. Ice is heating up to 0 degrees before anything happens to it. Now when I get to 0, I can begin to melt the ice. And what's saying time is increasing. During this time, I'm also adding heat is being added. So heat is being added at a constant rate along here. When I'm melting, I do have ice and water both. Both can be present at that temperature. The temperature is not going to change while I'm melting. Once that last piece of ice melts and turns into water, I'm going to begin changing the temperature again. My water will begin changing temperature as it increases. Once I get to this 100 degrees, that's the boiling point of water, again, I begin to vaporize. And I have water and steam, I should say liquid water. Liquid water and steam both present at the same time. Once that last bit of water turns into steam, now the steam can begin heating up again. Now Hess's law does apply to this also. We learned about Hess's law last chapter. You can add, it doesn't matter where you start, it's where you end. The starting and ending doesn't matter how many steps you take in between. So if I'm trying to find the enthalpy change over a long period, let's say I wanted to find the enthalpy change across here. I would have a enthalpy change for this one. I'd have an enthalpy change or heat added right here, and I would have a heat that would be added at this last part also. And these are all going to be different calculations because I have different C's for liquid and the C for steam are different. And across here I don't use the C delta T because there's no temperature change. I have to use the enthalpy of vaporization to calculate it. So if I'm trying to figure out with Hess's law, first you need to calculate the heat required to change temperature to that melting point or boiling point, whatever the problem asks for. But try to get to that point. Next, calculate the enthalpy change at the boiling point using delta H fusion or delta H vaporization. And lastly, this whole enthalpy change equals enthalpy of both steps. Whatever it took to get there, whatever it took to melt it. And if you have to, you can keep adding on to heating the next step up some more. So make sure you have that written down. Pause the video, go back if you need to. I'm going to show you one quick example here, and then we will spend some time tomorrow going over these a little more. If I have how much heat must be added to melt 15 grams of ice at 0 degrees. So I'm starting out with my ice, and I want to melt it. So I'm going to use Q fusion, or N delta H fusion, and my moles, 15 grams of water divided by 18.015 grams per mole equals 0.832 moles of water. So that's what I'm going to use instead of the grams. And I'm choosing that because it gave me per mole right here. So 6.02 kilojoules per mole. And that's going to equal 5.01 kilojoules. That's the energy required to melt the ice. Now once the ice is melted from 0 to 30 degrees, temperature change, I'm going to use NC delta T, what I used the last chapter. My moles, again, are the 0.832 moles. C, in this case, they gave me the 75.3 joules per mole K. And the temperature change is 30 degrees minus 0, so 30 degrees Celsius. This is going to equal 1,879 joules. Be careful when you're adding them together. Joules and kilojoules cannot be added. You have to change this to kilojoules by dividing by 1,000. Now when I add my total together, the total that it takes to take my ice, melt it, and turn it into a water at 30 degrees, I'm going to add those two numbers together and get 6.89 kilojoules. And that would be the energy required to melt that ice and heat it up. So again, enthalpy of fusion, enthalpy of vaporization are only happening at those phase changes, and we can use Hess's law to step through our phase diagram if we're given a temperature below a melting point that includes a state change. So we might have to use Hess's law to step through these different pieces of my phase change diagram. And that's all for now. We'll do another example in class tomorrow and get you guys practicing this on your own.